Hello, this is Keegan Goodell and my presentation for Lab 3 Circuits. First, the purpose of this experiment was to 1. Predict the behavior of the circuits and resistors in both series and parallel, 2. Measure the values of potential differences and conventional current in a circuit, and 3. Study the behavior of ohmic resistors and capacitors. As for the concepts covered, there was the loop rule, the node rule, current conservation, and circuits in steady state. Now, finally, the results. The current in the 2-resistor circuit was 0.02 amps, even when reversed. The time constant was 6.0024 seconds, which was very close to the expected value of 6 seconds. And in circuits with resistors, the higher the resistance value, the longer it takes to charge the capacitor. The procedure: first, connect the 2 batteries and record the ammeter readings for current 1 and current 2. Second, reverse the connections to one of the ammeters and record the reading. Finally, replace one of the ammeters with a voltmeter and record the readings. The results of this: in both cases, regular and reverse, the ammeter value was 0.02 amps. The broken circuit had an ammeter reading of 0 amps because the current wasn't flowing, and the voltmeter read 3 volts because of the 2 1.5 volt batteries in series. Now, to find the potential differences of each component, use the voltmeter and set it up in parallel with each component to check if the readings are accurate. The loop rule can be used, and it should give a total value of delta V round trip equals 0. And as you can see, the arrow is pointing. The math does equal 0. Data: using the potential different measurements, you can calculate the circuit elements using delta V divided by current. As you can see, the magnitude for the 47 ohm resistor was lower than the 100 ohm magnitude. And as you can see on the graph, or should have been better drawn, the 100 ohm should have a steeper slope than the 47 ohm. Now for measuring parallel ammeters, first place the ammeter in parallel to the 100 ohm resistor. With the ammeter in parallel, the current of the circuit should increase because the ideal ammeter has 0 resistance, so the current doesn't have to go through the 100 ohm resistor, and hence it will go through the ideal ammeter. So instead of a 0.02 amps reading, you should have a 0.06 reading. The second procedure: this part of the lab uses a 9-volt battery, 0.2 farad capacitor, and a 10 or 20 ohm resistor in the form of a light bulb. The battery will charge the capacitor in the circuit, and once it's disconnected, the capacitor will discharge. And the time it takes for the battery to charge and discharge the 10 ohm and 20 ohm light bulb will be recorded. As for important notes, in step 1, the charge of the capacitor was 0, so the light bulb was lit up. In step 2, the voltage was 9 and the capacitor is charged. And in step 3, the capacitor is discharged. Some of the time measurements with the images of charge 9 volt versus discharge 0 volts. And as you can see, the charge time for the 10 ohm to 20 ohm was about 2 times, and same with the discharge time, which shows that the higher the resistance, the higher time it takes to charge and discharge. As for the time constant data, the step involves a 9-volt battery, a 0.2 farad capacitor, and a 30 ohm light bulb. The capacitor is set to discharge and the voltage is read for 20 seconds. This voltage versus time data can then be plotted, as you can see in the top right corner. And as for the math, the slope of the graph is equal to -1 over time constant, where the time constant is the time constant of the circuit. -1 divided by time constant is equal to -0.1666, which is the slope. And then using simple algebra, you can see the time constant is 6.0024 seconds, which is very close to our expected 6 seconds. Before I get to the additional questions, I forgot to mention this earlier. It is written in an earlier slide, but the system of this experiment was the battery, circuits, resistors, and capacitors, and the surroundings of the experiment was everything else. As for the additional questions, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? A real ammeter does have some resistance value, and hence it would have a lower current reading. With the equation, current is equal to potential divided by resistance. You can see that as resistance increases, the current will decrease, and since the real ammeter has some resistance, it would increase resistance and therefore decrease current. For the second additional question, what if you're doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the current? How quickly Would our ideal model predict the capacitor to reach full charge, and would this happen in real life? It wouldn't happen in real life. The ideal model shows the capacitor would be fully charged immediately. However, in real life, the capacitor would not charge immediately because the battery has some resistance, which would slow the process down.